Okay, now we're going to build on our discussion of acceleration. And last time we just talked about acceleration. We said derivative of position, and then you differentiate it again, you get derivative velocity, you get acceleration. Well, now we're going to look at two components of acceleration. One component of acceleration is going to be parallel to the unit tangent vector, and the other is going to be parallel to the unit normal vector. So we're going to look at those two, and we're going to say this. We're going to say that acceleration in general. So if we talk about acceleration, we're going to say that acceleration consists of these two things. The tangential component times the vector. Now this a sub t is not a vector. Plus the normal component. And our job is going to be to find AT and A sub n. Okay? That's going to be our job. And the way I want to do it, I want to just sketch a curve here. Let's suppose that we've got, let me give myself a little more room. Okay, let's see here. Okay, so I'm going to sketch a curve like this. And what I want to do, let me make a little box around here. See if I can spin it around a little bit. Move it over. Maybe. Oh, there we go. I should have drew this in advance, shouldn't I? Okay, so now let's do this. Let me just move this over. I've got a little box here because here's what I want to do. Now let me rewrite this. Whoops. Okay, acceleration is the tangential component times t. Sorry. Okay, so let's suppose. Now, I drew this box here because what I want to do is I want to make a vector here. Okay, so here's a vector, and you can think of this as the velocity vector, and then I've got a vector over here, and you can think of this as a vector that's normal to velocity. Now, of course, this vector down here that I drew, this one right here, it's parallel to the unit normal, and this is parallel to the unit tangent. But what we have is we have another vector that is acceleration. So let me just put acceleration. I'll put acceleration out here. So here is the acceleration vector. So what we have here is we have this curve out in space. Something's traveling across this curve. And we want to talk about acceleration right here at this point, right here, at t equals whatever. Now, this right here, this part, let me draw this. This part right here, at the end of this box, I'm going to say that vector right there is going to be this vector. That right there is going to be the vector that's parallel to the normal vector. And in fact, this vector over here, this going up to here, is going to be the vector that's parallel to the velocity vector. Now, let's go through this, and I think you'll see how things work out here. What I want to do, I want to get the projection. Let me show you. I want to get the projection of acceleration onto the velocity vector. That's what I want to do. In other words, what I'm going to do is I'm just going to project that vector over here, because what I want to do is I want to find out what part of acceleration is going in the direction of the curve. That's what I want to find out. And then I want to find out, okay, which part of acceleration is going normal to the curve. In other words, I want to find out the things that make up acceleration. You add them together and you get acceleration. So I want to find this part here and this part here. I want to find this vector right here. Now, obviously, if I project this over, I mean, that's the way I would want to go, right? Just project it over. In other words, I want to get what part of this is going parallel to the velocity vector. So I want to project it onto velocity. Now, here's what you get when you do that. I get A dot V divided by the magnitude of V squared times V. Now, this right here is the projection. That's the projection. That's not exactly what we're looking for. When we talk about the tangential component of acceleration, that's not exactly what we want. Now, dig this. If I just do a little bit of playing around with this, and then write this as that, I didn't do anything wrong. You know, I'm an innocent man here. I just changed the way this order was. This right here, that scalar, that's the tangential component of acceleration. That right there, that's what that is. Now, you'll see a lot of times if you're talking about the tangential component of acceleration, it will be given to you in that form. So that's one way. So in other words, so let's see what we've got here now. We've got the tangential component of acceleration is A dot V over the magnitude of V. That's what that is. Now, that's not the only way you'll see this. But that's one. But you can use this. I mean, we could have projected acceleration onto the unit tangent vector, right? And then I guess we would have had A dot T, right? But this is something you'll see. So in other words, if you know velocity and you know acceleration, you can get the tangential component this way. So this is handy for us to look at. Okay, any questions about that? Okay. Now, what I want to look at now is this. So notice that this right here and this they're the same length, right? They're exactly the same length. So let me just put the AT over here, right? In other words, I know, so I'm looking at a triangle, okay? I'm looking at this triangle right here. This is AT, this is A sub n. That's the normal component of acceleration. Okay? The magnitude here, this is the magnitude of acceleration, that length. So what I have here is a sweetheart of a triangle, right? It's this thing. It's a nice right triangle. And I know A sub n, I know A sub t and I know the magnitude of acceleration. What I want to find is this thing, A sub n, which is the normal component of acceleration. So that is easy for us. That's easy for us to get because fortunately we took geometry and we know this. We know that A sub n squared plus A sub t squared is equal to the magnitude of A squared, right? That's what we know from geometry. I'm not interested in this relationship. I'm not interested in knowing what the magnitude of A is. I want to find out what this normal component of acceleration is. So I can just solve here. And if I solve this, what I'm going to get is the square root of the magnitude of acceleration minus A sub t. There. That's how we can get the normal component of acceleration. Right there. So you've got two well, you know how to find the tangential component and the normal component of acceleration. Those two formulas will give you each, right? Now, I want to point out something here. This is how we get the, this right here, that's how we get the tangential component for acceleration. Well, there is a way that we can get the normal component for acceleration with something that looks very similar. The normal component for acceleration is going to be A cross V, or let me do this. It doesn't really matter, but I'm going to do it in this order. Okay. So this might be helpful to you to keep them, to help you see that they're very similar. So the tangential component, you have a dot product up here. The normal component, you have a cross product. Now, you might be thinking, hey, I don't buy it. I don't see that this right here will give me the same result as this. I just don't buy it. Okay, so what I want to try to do is convince you. Now, in physics, probably they would give you one of these formulas. Maybe this one up here, or this one. I don't know which. But where I'm not focused on the physics so much is where these formulas come from. So I want to investigate this, and I'm claiming that this is the tangential component, I mean the normal component for acceleration. So I feel like I should at least convince you if you doubt me, because I don't want you talking about me behind my back. You know, he just throws crap up there. Okay, so let's think about this. First of all, let's think about this whole thing of the cross product. Okay, so I'm going to look at V cross A. And first of all, I want to remember this. Let's just think about this a minute. When we talk about the tangent vector, remember that the tangent vector is V over the magnitude of V, isn't it? It is, right? Because it's R prime over the magnitude of R prime. Well, that's that, right? A different name. So, dig this. I'm going to solve for V. And notice I have V is equal to the magnitude of V, T. Look at that. That's a true statement. Okay? That's true. Clearly. I mean, my goodness. There. Okay. Now, here's what I want to do. I want to note also, I want to remind you what acceleration is. Acceleration is the tangential component plus the normal component. So let's remember what acceleration is. Now, let's do this. So we're doing some preliminary work here, just getting ready I'm getting ready to prove this formula right here. Okay. What would this be? What is the T cross T? What is that equal to? Yeah, it's the zero vector, isn't it? Definitely. Because we've explored that before. When you cross product, in fact, if you cross product parallel vectors, you're going to get zero. So we know that this is the zero vector, and of course the magnitude of that is zero. Now, what do you think about this? What is the the unit tangent vector crossed with the unit normal vector? What do you think that is? The tangent vector crossed with the normal vector. What is it? Yeah, that's right. That would be 1, wouldn't it? But look at this. But still, that's kind of, if I said no, that's not the case, I don't know if you'd know how to refute. In other words, I don't know if you know that for sure. But remember this. Remember we said this. We said that the magnitude of, well, let's just go to just general vectors here. The magnitude, and let me not use A, let me use U and W. We said this, when we started exploring the whole thing of cross product, we said, well, that is equal to the magnitude of u, the magnitude of w, times the sine of theta, right? This was a property that we looked at. Okay? This was definitely a property we looked at. Now, what is the angle between T and N? 90, right? So in our particular case, what we have is, let's look at this a minute now. Let's just put in our values here. We have T cross N, and let's put this in. We have the magnitude of T, magnitude of N, times 1, right? See, sine of 90 degrees is 1. So there's what we have, right? Now, this proves what you said, right? Yeah, it's the magnitude of this, because this is 1 and this is 1. So it looks like the magnitude of T cross N is 1. Ah, okay. Now, so let's see what we have here now. We have V cross A. Let's just start there. Now, that right there is the magnitude of V, T, right, cross A. And what is A? Well, A is AT, T, plus AN, N. Y'all see that? Let me Crayolicize it. V, V, A, right? Now, we then go back to a property of cross products here. That it works pretty much the way you think it would. Kind of a distributivity thing, isn't it? So here's what we have. This, so here we go. We've got the magnitude of V times AT times T cross T, right? In other words, I just pulled out the constants. And the magnitude of V and A sub T, those are just constants. Plus, now I've got, over here, I've got the magnitude of V, AN, and then I've got T cross N. Y'all dig that? Ah, look at this. What is this first part? 0. Ah, 0. So it looks like this. Oh my goodness. Did it just reduce to this? I can't believe what I'm seeing here, that this whole thing just reduced to this. Okay? Now, okay, so that's what we have now. Now, let's magnitude. So now, if this is V cross A, then the magnitude of V cross A is equal to this, right? So now, and this is a big N here. Now, I can divide by big N. I mean, I can divide by the velocity, and I get this. You see that? And that's exactly what we said. You know, I said this, and y'all were scoffing and doubting. But yeah, it's true, isn't it? There's no question about that. Okay, so this is another way that you can get the normal component of acceleration. That's another way you can get it. Okay, any questions?